Hello Q-steppers and fellow R coders, and welcome to another tutorial in the series of How to in R. This tutorial will cover how to compute correlation assessments on numerical variables in R. So what is correlation? Correlation is examining whether our variable X is related to variable Y, or how our X and Y variables move together. We can reveal if the variables have a positive or negative relationship, and if they have a weak, moderate, or strong relationship. Now, you may have heard someone say correlation, not causation. This means that we cannot imply that as our variables have some sort of relationship, that one causes the other, or vice versa. Remember, we are analysing how our X and Y variable move together in isolation without taking other factors into account. So when we conduct a correlation test in R, we are provided with a p-value and a coefficient. The coefficient is bound between the value of -1 and 1. This notation provides us with the direction of the relationship. Then with the value, we can make inferences to the strength of the relationship. It is weak, moderate, or strong. Let's run some simulated correlation scatter plots. So these are ideal correlation types, but with real life data, we will probably never see them as close as this. So the first is a perfect positive correlation with the coefficient R value of 1. So from this graph, we can imply that for every increase in the X variable, we have an equal increase in Y. This graph represents a perfect negative relationship with a coefficient of 1. We see for every increase in X, there is an equal decrease in Y. Let's have a look at a coefficient of 0. So this plot shows that for every increase in X, Y basically just stays the same. So therefore, there is no relationship. Another example of zero correlation is this V shape that implies that Y is unrelated to any changes in X. Okay, so to execute a correlation test in R, we use the core.test function. We then place our X and then Y variable. We then use the use equals complete observations argument to let R know to take out any missing values. So let's have a look at this output. So we have the name of the test. We have the variables that we are testing. We have the t-value, the degrees of freedom, and the p-value, which is under the 95% level of confidence here. It then states the alternative hypothesis, which would be there is a statistical relationship between income deprivation and crime in Scottish data zones. We then have the 95% confidence intervals. We then have our correlation at the bottom. So as our p-value is under the 0.05 level of confidence, we can therefore reject the null hypothesis and conclude that there is a statistical relationship between income deprivation and crime rates in Scottish data zones. Now that we know it's significant, we can give interpretation to the correlation coefficient, which is 0.34. So we know from this, it's a positive relationship, but how strong is it? With a value of 0.34, we can say a weakly moderate relationship. The usual notations used is 0 to 0.3 is a weak relationship, 0.3 to 0.7 is a moderate relationship, and over 0.7 is a strong relationship. Okay, so by knowing the coefficient is 0.04, we can square this to find out our R squared, or the variance. So we square this and times it by 100. This lets us quantify the amount of variance explained in our outcome variable from the predictor variable. So we have an R squared of 11.56. This means that we can infer that 11% of the variance in income deprivation is explained by crime. Let's do another example. Let's keep the income deprivation variable and now include the employment deprivation variable. Okay, so our p-value is under 0.05. So there is a statistically significant relationship between income deprivation and employment deprivation. Our correlation figure is 0.96. So we have a very strong positive relationship. Let's find out the variance. Our R squared is 92. So we can further add that 92% of the variance in employment deprivation explains income deprivation. Let's do one more example. Let's analyse whether we have a statistical relationship between the crime rate in Scottish data zones and the rate of school children who attend school 90% or more of the time. Okay, our p-value is under 0.05, so we can reject that null hypothesis. Our correlation is minus 0.37, so we can therefore infer that we have a negative moderate relationship between crime rate and school attendance in Scottish data zones. We can further add that as crime rates increase, we can expect school attendance to decrease. Let's carry out a Spearman's correlation. We would use the Spearman method if our data are non-parametric. So instead of assessing a linear relationship like in Pearson's above, the Spearman correlation assesses the monotonic relationship, whether it's linear or not. Let's have a look at the code. It's almost identical to the Pearson's. However, we use the method equals Spearman function. False argument to avoid a warning message as some data zones may hold the same value. Let's have a look at that output. Okay, so our p-value is under the 95% confidence level. Instead of having R at the bottom, the correlation is denoted by rho. Minus 0.55, which is slightly stronger than the Pearson's correlation. So we can therefore infer again that we have a negative moderate relationship between the two variables. So which one you decide to use will depend on your data. And remember, when visualizing the relationship, state which correlation test you've carried out. Hopefully this tutorial has got you familiar with Pearson and Spearman correlation. And remember that correlation does not imply causation. So happy coding, QSteppers, and remember to subscribe to your social media channels, and thank you for watching.